Welcome to our physics lesson. My name is Nicholas Okuthe. We want to look at a topic called floating and sinking. I have analyzed the topics and categorized the key tested areas into 5. One is on Archimedes principle, next is on upthrust, law of flotation, then relative density, lastly the application of floating and sinking and Archimedes principle called hydrometer, though there are so many applications, but we'll dwell so much on the hydrometer. We start with Archimedes principle, and we say that Archimedes principle states that when a body is partially or fully immersed in a fluid, it experiences upthrust equal to the weight of the fluid displaced. It means that upthrust is equal to the weight of the fluid displaced. Fluid here is a liquid or a gas. So when you immerse a solid, it may be in water, then the volume or the weight of the water displaced will be equal to the upthrust that this body will experience. Archimedes carried out an experiment, and this experiment can do it to verify the truth about this principle. So the apparatus are as listed there: a flow can, metal block, a beaker, a spring balance, a string, and some water in a eureka card. The procedure is first we weigh the object in air, that is the exact weight of the body, using a spring balance and record that weight as W1. Then the next step is we immerse the block in water in the overflow can. The overflow can has some beaker under the spout there where you can collect the displaced water. Then next, now we record the weight of the block when fully immersed in water. So we have recorded the weight in air, now the weight in water. This weight in water, we also call it apparent weight. So apparent weight is the weight when it is in a liquid. Weight of any object in a liquid, call it apparent weight. And objects tend to weigh less when they are immersed in a fluid. So we expect in this case W2 to be less than W1. The weight in water will be less than the weight in air. And what causes that is upthrust. Then the next step is we measure the volume of water displaced and calculate its weight. When we have the volume and we know the density of water, we are able to calculate its weight. So its weight, we'll record it as W3. So we'll be getting what we call apparent loss in weight. Apparent loss in weight is the weight in air minus weight in the liquid. Like weight in air, W1 minus weight in water, W2. Then also we get upthrust, where upthrust here will be the same as the value W3. So when we do comparison, W1 and W2, we compare with W3, then we realize that W3, which is upthrust, is equal to the weight in air minus the weight in the liquid. So this upthrust, we also call it apparent loss in weight. So apparent loss in weight, which is upthrust, is normally weight in air minus weight in the liquid. But because mathematically we have proved that W3 is equal to W1 minus W2, then we also learn that upthrust is also the same as the weight of the water displaced. So from there, we end up showing that or proving that upthrust depends on two things. One, the volume of the fluid displaced. Then it will also depend on the density of the liquid or the fluid displaced. So it depends on density and volume of the fluid displaced. Now, upthrust itself, we define it in Form 1 under types of forces as an upward force that acts on the surface of the liquid. It is an upward force, meaning the direction is upward. So when you immerse maybe an object in a container of water, then you see water splashing upward. That is because of upthrust. It is the upthrust that makes the water to move or splash moving upwards. So we have learned the two formulas for calculating pressure, upthrust, and we must have this at our fingertips at any point. The first and the most important formula is that upthrust is weight in air minus weight in a fluid. So when you can measure the weight of an object in air, which is its actual weight, and then the weight in a fluid, then the difference between the two gives us upthrust. The second formula of upthrust is rho Vg or V rho G, where V is the volume of the solid or volume of the fluid displaced. Remember, in displacement method of determining volume, when an object displaces water, then the volume of water displaced is the same as its volume. Then the second constant here is density. Density of the fluid displaced. If it is water, we use the density of water. If it is alcohol, we use the density of alcohol. If it is oil, we use the density of oil. Then G is the gravitational acceleration. So these two formula are the most important formula in this topic that you must understand before you can do any calculations regarding problems in this topic. Now, we are also getting to learn that when a solid is immersed in a fluid, for example, you take a stone, you are trying to immerse it, then the upthrust will be increasing from 0 to the maximum value when the fluid is totally immersed. So when the fluid is now when the solid is fully immersed in the fluid, then upthrust will be maximum. So upthrust increases as the solid gets gradually immersed in the fluid. Now, when the fluid is now fully immersed in the fluid, then what happens? Upthrust remains constant even if you increase the depth or you increase the volume of the fluid. The upthrust remains constant. That can be summarized using a graph like this, a graph of upthrust against depth of the liquid. So you can see that upthrust is increasing gradually or not uniformly up to some point whereby it is fully immersed. So at that point the object is fully immersed, and any increase in depth or increase in volume of the liquid does not cause an increase in upthrust. Upthrust remains constant. So meaning where the graph starts to flatten, that point is where the solid is fully immersed. And at times maybe you may be asked to get upthrust when the object is fully immersed. So you only check at the point where the fluid or the graph starts to flatten. So at that point, any increase in depth does not cause an increase in upthrust. We look at something on relative density, though we can also deal with it after looking at what we call floating. According to Archimedes' principle, relative density, first we define it as the density of a substance, the ratio of density of a substance to that of water. When you take the density of a substance, then you divide by the density of water, you get what's called relative density. So it's the ratio of the density of a substance compared to the density of water. Being a ratio, it means it doesn't have a unit. For example, you take maybe alcohol whose density is 800 kg per cubic meter, you divide by the density of water, which is 1000 kg per cubic meter, you'll get 0.8. So the 0.8 becomes the relative density of alcohol. Now, according to Archimedes' principle, relative density of liquids and solids can be calculated using various formulas, but the most important or common formula that we use for a solid, relative density of a solid is the weight of the solid in air, which is just the same as its actual weight, divided by upthrust in water. So meaning if I can have the weight of an object in air, then I have the weight in water, then I can get upthrust in water, then take the weight, I divide by upthrust in water. For a liquid, relative density is upthrust in the liquid over upthrust in water. So I must have the upthrust in that liquid, I also get upthrust in water, then divide the two, I'll get the answer with no units because it is a ratio. For example, look at this example, an object weighing 1.04 Newton in air and 0.64 when fully immersed in water and 0.72 when fully immersed in a liquid. If the density of water is 1000, find the density of the liquid. So because we want to get the density of the liquid, we'll get upthrust in the liquid, where upthrust in the liquid is the weight in air minus weight in the liquid. So 1.04 minus 0.72, which gives us 0.32. Then we get also upthrust in water. Upthrust in water is the weight in air minus weight in water. 1.04 minus 0.64, you get 0.4. So because density of a substance in a liquid, or relative density of a liquid is upthrust in liquid over upthrust in water, we take upthrust in the liquid, which is 0.32, divide by upthrust in water, which is 0.4. If you divide that, we get 0.8. So that becomes the relative density of that liquid becomes 0.8. So if I need the density of the liquid, then I'll take 1000, I multiply by 0.8. So it will give me 800 kilogram per cubic meter. So after getting relative density, To get the density of the liquid, I take the relative density of that liquid, I multiply by the density of water. Yeah. Look at also this one. A stone of weight 3 Newton in air and 1.2 Newton when totally immersed in water. Calculate the volume of the stone. So for me to get the volume of the stone, I must get upthrust. And upthrust here will be the weight in air minus weight in water. So weight in air 3 minus weight in water 1.2, I get 1.8. So that is the first one for getting upthrust. The second formula for getting upthrust is rho Vg. So I equate 1.8 to rho Vg. So upthrust, which is 1.8, will be equal to volume V, I don't know, times 1000, which is the density of the liquid water, times 10, which is the G. So I'll get the volume of the liquid to be 0.00018 cubic meter. But because the question wanted number 2, the density of the stone, density will be its mass over its volume. If its weight is 3 Newton, it means its mass would be 3 divided by 10, which is 0.3 kilogram, over its volume, which I've worked out to be 0.00018. So if I divide that, I get the density of that stone to be 666.67 kilogram per cubic meter. Thank you very much. We want to end there. We'll proceed in the next lesson.